Hello, and welcome back to CS300. This is our final chapter 7 about algorithmic paradigms. These paradigms convey some generic approaches in order to design efficient algorithms. They are not exclusive. They can they're not exhaustive, but they can provide valuable insights and ideas when you're faced with the challenge of devising an efficient algorithm. So we're going to talk about divide and conquer approaches and algorithms. We've seen several examples already, and now we're going to take the general perspective and abstract view on divide and conquer algorithms. We will talk about the dynamic programming. Again, we have seen several examples of dynamic programming algorithms. And here we're going to look at the general perspective again. Then we will look at greedy algorithms. We also have seen some greedy algorithms, maybe without having spelled out that term explicitly, but we have already learned examples of greedy algorithms. We'll talk about backtracking algorithms. In this course, we have not really discussed example of backtracking algorithms, so this is a perfect opportunity to discuss backtracking approaches. And we will discuss branch and bound algorithms. Again, not something covered so far in this course, so it's important that in the final wrap-up chapter 7, we mention this approach. So this is the some basic principles. And again, let me emphasize that they're not exhaustive. There are other approaches to design algorithms, although they're not disjoint, they're not exclusive. One can combine several of these approaches when designing efficient algorithms. So let's start right away with the first algorithmic paradigm, divide and conquer. And you have seen such examples, for example, when we devised algorithm for polynomial multiplication. We discussed the Karatsuba algorithm, we discussed Toombs algorithm, we discussed the Cook family of algorithms. All these proceeded by dividing the original problem, the polynomials to be multiplied into blocks, then multiplying these blocks recursively, and then recovering and combining the results from the recursive calls to construct the solution to the original undivided problem. And this is a perfect illustration of the general divide and conquer approach. So let's take an abstract view on that. We're given a problem of size, let's say n, and we're supposed to produce a solution to this problem. Let's call the size of the solution m. And the algorithmic approach of divide and conquer, here you see the rectangle representing the algorithm we're supposed to design. And the idea is to divide the original problem of size n into subproblems. In Karatsuba would divide into 3 subproblems. Tomb would divide into 5 subproblems, polynomial multiplication, and Cook would divide into a K subproblem, and that's also the idea for the general approach. Divide the original subproblem into some arbitrary suitable number K of subproblems, each one having its own size. For example, here we have a subproblem. First subproblem has size 1 and 1. The second subproblem may have size n2, and so on. And the K subproblem may have size nk. That's just to be as general as possible. And then consider the solutions to these subproblems individually, separately. So the solution to the first subproblem may have size m1, solution to the second subproblem may have size m2, and so on up to the solution of the K subproblem having size mk. That's the approach, and now we need to fill in the algorithm, of course, right? Maybe the algorithm proceeds by solving each subproblem separately, recursively. That's the essence of having subproblems, to make them independent, smaller problems, make a recursive call to the algorithm to solve these subproblems. And you see from the picture, indeed, the subproblems with input and output, NK and MK, are indeed of the same type as the original problem. That's the essence of divide and conquer design, finding these subproblems. That's the ingenuity of Karatsuba, of Thum, and of Cook, and similarly for matrix multiplication, which we also, the Strassen algorithm, also based on divide and conquer, dividing the original matrix into a smaller matrix and then performing multiplication of the smaller matrices. So that's a recursive step. But divide and conquer also requires first dividing the problem and finally combining the original solution. So there's a subdivision phase in a prototype divide and conquer algorithm indicated here, which also take some computational costs in order to algorithmically create and kind of carve out the subproblems from the original problem. The polynomial multiplication example, this was consisted in dividing the original polynomial into these independent blocks. And then there's the recombination phase in the divide and conquer algorithm, where the results from the individual subproblems are used to recover the solution to the original problem. In the example of polynomial multiplication, this involved some adding of polynomials which had some overlap, if you recall. So that's a general scheme of a divide and conquer algorithm. And this general scheme leads to a generic recurrence for the cost analysis of a divide and conquer algorithm, namely the cost of the algorithm on input n is composed from the cost of the subdivision phase, which in general may also depend on n, plus the cost of the individual recursive calls, depending on the different sizes, plus the cost of recombination. And yeah, in the example of polynomial multiplication, the subdivision phase would have linear cost, and the recombination phase would also have linear cost, and thus the overall cost was dominated by the 2, 3, 5, or generally k recursive calls. So this is about divide and conquer design, and the analysis of such a divide and conquer algorithm then becomes kind of straightforward. Examples we discussed are repeated squaring, right? So like raising some quantity to a high power by first raising it to the half of the power recursively, and then combining it depending on the parity of the exponent, also perform one additional multiplication. So here's the recombination phase. Also Fibonacci, we had the most efficient Fibonacci algorithm based on repeated squaring of the matrix, another example of a divide and conquer algorithm. Polynomial multiplication, I've mentioned as a great example, the naive algorithm, Karatsuba, Thum, Cook, and so on, all divide and conquer algorithms, and matrix multiplication algorithm due to Strassen, and all the improvements that have been devised since then, up to and including the current world record. So that's concludes our discussion of the divide and conquer paradigm for algorithm design. Let's now move on to the next paradigm, dynamic programming. Again, we've seen many examples of dynamic programming algorithm, such as the Wagner-Fisher algorithm, to the longest common substring algorithm, where the original problem finding a longest common suffix, some longest common substring, is generalized to the more general problem of finding a longest common suffix. and then share suffix that is shared by the initial segments. So the general idea dynamic program is again decomposing the original problem into a family of smaller problems, but that climb up and include the original problem. So here the subproblems here are indicated by this table with two indices. And filling this table, then the final last entry contains the solution to the original problem, whereas the individual entries of the table are easy to compute based on and combining previous entries of the table. So this is kind of a algorithmic perspective on structural induction. Here in case, induction with two parameters, I and j. So and corresponding to this structural induction, here two parameter induction, filling this table algorithmically proceeds by first filling the topmost row and the leftmost column. And in case the table has more dimensions, that includes more initial conditions, right? So like induction start, and then gradually filling the table in using induction. Here the example is the I plus first and j plus first entry could immediately be easily be calculated based on the ith and jth entry with a simple case distinction, which is implemented with the if then else clause in programming. Yes, I mentioned the Wagner-Fisher algorithm for computing the edit distance, which is also a dynamic programming algorithm. Instead of computing the edit distance of the original strings, one generalizes this to compute the edit distance of all possible initial subsegments of the strings. So this is a more general problem, which includes the original problem as the case when I and j are equal to the length n and m of the original problems. And again, the induction starts are easy. The leftmost column and the topmost row can be filled in immediately with a loop in an algorithm, and the induction step corresponding to the algorithm gradually filling the table again proceeds by a simple case consideration, if then else, and based on the entries of the matrix previously filled entries corresponding to the induction step in mathematical induction. Generally speaking, the idea underlying dynamic programming is to decompose the original problem into overlapping subproblems. Maybe this is an essential difference to divide and conquer, where the subproblems are preferably independent so that they can be solved recursively. Whereas in dynamic program, the problems should be overlapping as much as possible, so that the next climbing up to the next subproblem only involves little additional overhead based on the information that has already been calculated for the subproblems, such that the optimal solution to the original problem is simply a combination of the subproblems. So that concludes our discussion of dynamic programming. Greedy algorithms is our third paradigm. In greedy algorithms, we also consider, let's say, some examples, namely the lightest path problem in a given weighted path. Here, our heuristic, which we've turned into an algorithm, was to repeatedly follow the cheapest edge until arriving. So this is a kind of Dijkstra's algorithm, which may not yield the lightest path, only following the cheapest. So this is a heuristic in general, but may not yield an actual algorithm. And the question of which problems allow for greedy algorithm is a very intricate question. Let me illustrate that with a positive example, namely a cashier's algorithm, for the change-making problem. So change-making problem is the following. Suppose you're asked to pay a certain amount, and you have a collection of coins or bills of various values in your GGAP. What's GGAP in English? Wallet. And how can you compose a certain value from this combination of coins and bills with repeatedly using, for example, you can use 20-cent coin repeatedly, but at the end you're asked to use the least number of coins and bills. Okay, so for example, you can make a value of €1 by using 20-cent coins 5 times. That means 5 units of a currency, but you can also make €1 by using one single coin of value €1, which is the preferable solution to the cashier problem. And the solution that to this problem that you all have in your mind is to start with the largest coin or bill that is smaller than the value, and to put that out and then repeatedly try the same with a reduced amount. And but why does this work, and for which choices of coins and bills does that even work? For example, in the United States, there's a 25-cent coin, and in these cases, the cashier's algorithm is not guaranteed to yield the optimal decomposition of the original amount into least number of coins and bills. So it's really an intrinsic property, and actually it's part of the design of Korean and of Japanese and of European currency. That the cashier's greedy algorithm indeed is an optimal algorithm, whereas the United States-based currencies, the cashier's algorithm may not be optimal. Another example for greedy algorithm is the one we've encountered, the Huffman tree construction, which is also a minimization problem. And here the algorithm, recall, would repeatedly extract symbols with least frequencies and then combine them to a larger symbol. And that's also kind of a greedy or naive or straightforward choice. Like cheapest edge in the graph problem, largest currency in the cashier's change-making problem, symbols of least frequencies in the Huffman problem, but only in the last 2 cases, these greedy algorithms actually yield the optimal solution, which indicates that only certain problems allow for greedy algorithms. So one way of trying to formalize this is deliberately vague, but one way of looking at what makes up for a greedy algorithm is to make whatever choice seems best at the moment and proceed to solve the subproblems that arise later without reconsidering previous choices. That's how the algorithm book has formalized what means for greedy algorithm, but of course this is a very vague kind of definition. This is just some guidance for you for looking at the many algorithms that we've encountered in this course and that can help you when you're asked to devise algorithms yourself later. Backtracking is an algorithmic paradigm that was not covered and for which we don't have actually an example in current CS300. So, but let me still try to explain it. So the basis of backtracking is to incrementally build better and better candidates to the solution and abandon a candidate as soon as a better candidate has been found. A simple version of this is looking for the maximum element in an array. So we look at the first few elements, take the largest element as a candidate maximum, and then we look at the next element. If that is larger, then we abandon our previous candidate and replace it with a better one. But looking for a maximum in an array is kind of a trivial way and linearly going through the array. In general, the backtracking applies to an implicit so-called search tree. So here's, for example, a search tree searching for a path in a maze. And you see always one path emphasized in this tree. The tree is only present implicitly. Some of the paths lead to dead ends, and only one path leads to the goal, to the solution, like this here. And finding that means an algorithm running into different dead ends, backtracking from that, and then trying in a different direction, possibly again running to dead end, until finally finding the optimal solution that comes, that actually reaches the goal. So that's our final paradigm of backtracking. And to wrap things, branch and bound, yes, branch and bound is a related paradigm. So here we have a tree whose weighted nodes are supposed to be heap ordered. Heap ordered is a concept that will become important again later in CS500. So let's formalize that here. A tree with weighted nodes is heap ordered if the weight of any node is no less than that of its parents. Here's an example. Here you see a tree, and there are nodes, and the nodes are assigned weights. And the weight of any node, like here 11 of this node, is no less than the node of its parent 2, no less. So same here, the weight of 12 is no less than the node of its parent 11, and so on. So this is not to be confused with the search tree. A search tree means that the nodes to the left child must have weight or key less than the key value of the parent, which must have key value less than the right subtree. But here it's not left, not left root right, but instead it's bottom up, so that the root will always have the least value, and the goal of a problem is to find the lightest leaf in such a heap ordered tree. So here we're interested in leaf, and the example algorithm is to recursively traverse that tree, and once keeping track of the lightest leaf, like with the maximum search, and once a certain subtree has been identified to have a root which already exceeds the current least weight candidate, then there's no need to recurse into that subtree, because by the heap order property, it means that the entire subtree, not just the root, but also all of its children and children's children, will all have a value which is already larger. So there's no need to recurse into that part. So that's a generic idea of a branch and bound algorithm to generalization of this maximum search algorithm to search in a tree, which is a popular approach to, for example, game trees like in chess or Go, traditional Go without artificial intelligence. Okay, so that's our final paradigm, branch and bound. The branch part is to recursively traverse the tree. The bound part is to cut off or to refrain from recursing into certain subtrees that are already known to be irrelevant and that are known to not contain a better solution. So to summarize this very short chapter 7 on algorithm paradigms, we've talked about divide and conquer algorithms illustrated with examples like polynomial multiplication and matrix multiplication algorithms that we talked about in the few first chapters of this lecture. Also, quicksort is a divide and conquer algorithm. We talked about dynamic programming algorithms, again illustrated with examples such as the longest common subsequence problem and the algorithm we considered, or the edit distance problem in algorithm. Then we talked about greedy algorithms, greedy type algorithms, which include, for example, the Huffman tree construction. And we talked about backtracking algorithms and branch-and-bound algorithms, for which we didn't have examples in the current course, but we had the examples in the corresponding subsections of chapter 7. So, and that concludes our last chapter, chapter 7 of Introduction to Algorithms. And again, we're going to have a small pause and then look at the overall course contents to summarize. Introduction to Algorithms, CS300. Where in the first chapter we talked about computational problems and algorithmic solutions, after having in the kind of zeros chapter talked about the underlying virtues of computer science, which include problem specification first before starting coding, semantics and operational primitives that we can use, that we're allowed to use, then cost analysis in as opposed to empirical absolute running time performance measurements. And we talked about correctness proof of correctness, and proof of optimality, that is complexity theory. And we've illustrated these principles with computational problems and algorithmic solutions to very simple problems, namely Fibonacci numbers and polynomial multiplication and matrix multiplication. And we've talked about search problems and their variants, such as, for example, calculating the statistic like the median and its variance. We talked about sorting problems. There is comparison-based sorting algorithms and non-comparison-based sorting algorithms, including radix sort. Then we talked about data and data types and how they build up from single bits up to more complicated data types, including linked structures. We talked about graphs and graph problems, various algorithms involving graphs as linked data structures. We talked about string problems and string algorithms. And finally, we talked about algorithmic paradigms, generic approaches to algorithm design problems. So that's all for CS300. Thank you very much for your attention. I've had a great time teaching that algorithm. You have been a wonderful audience.